Welcome to this next video in the DIDCOMM Superstack series. Um, this one focuses on prototype 5, and we're going to be very sort of tactical here, and we're going to introduce a concept called the Structured Credential Programming Model. And we're going to just look at a very focused piece of code, but there's kind of several layers to the programming model. We start by modeling, for example, a verifiable capability authorization using TSL. We get a bunch of auto-generated classes and constructors automatically created for us, and then we'll create some helpers or wrappers around those. So we'll model a VCA using TCL. We'll do the automatic code generation. The dummy VCA that we've been using in prototype 2, 3, and 4, just the boilerplate JSON, we'll replace that with the VCA that we're creating programmatically now using the Structured Credential Programming Model. And let's go ahead and see what that looks like. Just as a reminder, when we look at the Structured Credential Programming Model, it actually is an envelope, or the envelope is a metaphor. So this is a sealed envelope. It's an envelope that contains content. It has a label containing metadata describing what's in the inside the envelope. So this would be things like the verifiable credential type, and then the envelope is closed, the flap is closed, and a seal or a proof is attached to the outside of the envelope. And this is how we can detect if any of the contents have been altered, if the seal has been broken. So let's go look at some code now. This is going to take a little while to explain. There's a few moving parts. We're really just focused on this, about 12 lines of code. And what we're going to end up with at the bottom is a piece of JSON representing a verifiable credential or capability authorization. We actually create the VCA here in this helper method by passing in a few parameters that are specific to a VCA. Things like what is the list of rights, the list of restrictions, the list of processing options. We need a key for who is offering this VCA. In this case, that's Charlie. And we need Charlie's secret key to actually create the proof. So we look that up in the key vault. And also we need to have the key of the person that we're granting this VCA to. And so this is Delta. So the use case, if you will, is Charlie creates a VCA offering specific capabilities for a specific VC to Delta. And the VC we don't actually have to deal with, but we do need to have a DID that represents that VC, and we're generating that up there. So this is looking from sort of the top down in terms of the top level programming model. Let's run that and look at the JSON that's created. And that'll sort of act as bookends then, and we'll look in between to see how do we get from one to the other. So I'm just going to start this up, and we're just going to look at this one piece of code. We're not looking at the entire DIDCOMM agent. So we're using TSL a lot more than we did before, so there's some extra TSL classes being created. We're now actually building the project, and it'll start up here in a moment. Cool. So we've invoked the new VCA credential helper method, and it's returned a VCA. And if we look at the VCA, it's following our structured credential model. You can see envelope and labels and a few things like that. You can also see that realized here in the JSON serialization. Remember, toString executed against any TSL-derived class will automatically produce a JSON serialization for it. To make this a little more clear, I ran it earlier and brought it into Visual Studio Code so that we can look at it. So I've collapsed a number of sections, and this is just to emphasize the structured credential model. So what we're seeing here in its entirety is a sealed envelope. How do we know it's a sealed envelope? Because it has an envelope element, and because it has a proof. That's what we call the seal. If we look at the envelope, it has an identifier. It's the DID key identifier that we created earlier. It has a label, and the label has things like the type of verified credential. This is a verified credential authorization, version, what the trust level is, and so we're using an Oberon proof to generate the proof, whether it's encrypted or not. We have a text here, some text describing the name, so we're just saying it's VCA and its identifier, and we can have an array of comments. Because this is a VCA, we don't have an overarching VCA to control access to this VCA. That's just a version 1 sort of thing, but in the fullness of time, VCAs, because they're verified credentials, would also have VCAs. Okay, so that's the label that's on the outside of our envelope. If we look at the content consists of the subject ID, context, everything that's needed to describe the data, and down here we have the claims. And so these are the claims that make up the credential, and there's the VCA type. So this is a proclamation. We're proclaiming certain rights, restrictions, and processing options. There's the subject. That's the VC. This is the DID key of the VC that we're granting, that we want to grant these rights to. Here's the DID key for Delta, the entity that we want to give the rights to, and here's the caveat. The caveat encapsulates the rights, restrictions, and processing options that are available to Delta to work against this particular subject ID. So that's what we're trying to create. That is a structured credential. Again, the main parts being the claims and additional descriptive information, data-related descriptive information make up the content. The content is a key part of the envelope. The envelope also has a label that we saw before. We think of that as the metadata. If we take an envelope and have an associated proof, in this case we've got a hash thumbprint, and then we have a proof running against that hash thumbprint. So a combination of the envelope and the proof gives us what we call a sealed envelope, aka a structured credential. Okay, so let's look at how do we start building that. So let's stop this. So far we've seen TCL being used to model the DIDCOMM agent as a server with protocols having messages being built up of structures. We created that in prototype 1 and have used that throughout. We're now using TSL in a different domain. We're using it to describe a structured credential. So here's where we see that we've got a structured sealed envelope. This is a particular sealed envelope for a VCA. That's just a naming convention we've adopted. And just like I was showing you in the generated JSON, the JSON that was generated is a direct result of this model. So it's not surprising that we see that the sealed envelope consists of an envelope and a proof. The envelope is defined up here as its own structure, and it contains the UDID, the label, and the content, just like we saw in the JSON. The envelope content consists of the context, or excuse me, a DID, the context, the credential subject key, and the claims, and optionally you can have encrypted claims. We're not using that feature or not using that capability. And we can see that the claims are defined up here. There's the VCA type, the parent, the subject, the granted key, and the caveat. Exactly what we saw over here when we drill into the content and we drill into the claims, and there's the caveat. So the claims consist of those 4 properties, and the caveat consists of those 4 properties, and those are derived directly from the TSL definition we're looking here. Some of these elements, such as proof, you can see are defined in a generic definition. Anything that's common from one credential to another, to another, to another, where the structures are common, we keep those in a separate TSL file. So here we can see an envelope seal doesn't change from one definition to another. The structure of a packing label doesn't change. And so we've defined those in a separate file here. So here's the packing label, all the different fields that a packing label can have, and here's the seal. There's the hash thumbprint, and there's the proof. We could also have different kinds of proofs and additional optional fields. And so the way that this generic credential TSL file gets referenced here is it does have an include capability here at the top. So very easy to do the modeling of arbitrary structures. In this particular example, we're using TSL to model the 4 components that make up a structured credential: the sealed envelope, the envelope itself, and the envelope content, and finally the claims that are inside the envelope content. And we just simply hit build, and if you look down here, you'll see a bunch of different C# classes being generated and constructors being generated, and we make use of those over here in the Credential Factory. So in the Credential Factory, what we want to do is look at one particular method here, the one new VCA credential. This is the one that we called over here new VCA credential to build our VCA. So as you can imagine, we need to build each of those 4 parts. And so we pass in all the parameters that make this VCA unique, the things that we have to stuff primarily in the claims. So here we're going to create a new DID for this VCA, and we're going to use the intrinsic OK API DID generate method to get a key, because we need to get a key for the VCA. Then we're going to create the claims. Again, we have an auto-generated class and constructor that knows how to create and populate the claims. It takes, if we look at the constructor, the declaration of the constructor, it takes an ID, it takes a list of rights, it takes a list of restrictions, a list of processing options. So we're passing those in as they were passed into us in the new VCA credential method. So that gives us the caveat. Claims, again, is made up of the proclamation, the subject VC that this VCA is to be applied to, the granted key, who is the person who's supposed to receive this, and then, of course, the caveat. Exactly what we saw here in the definition of our claims. So model gives you a bunch of constructors, and away you go. So once we have the claims, we want to take those claims and we want to start stuffing them into the envelope. So we're going to take the credential ID and the claims, and we're going to stuff it into this intermediate structure called the envelope content. So again, this is auto-generated. Envelope content, if we look at it, it has the context, the subject ID, and the claims. This is standard really across all credentials. We're going to create an instance of the content. And then the next thing before the operation of stuffing the content in the envelope and placing the packing label on the outside is a single operation. So we need to create the packing label. We create the packing label here using the generic packing label constructor, and it takes the verifiable credential types. It takes what kind of proof or trust level we're using, the encryption flag. It takes the name, and then it takes the lists of comments, etc. And so once we get the label here, and to build up the label, one of the things we need is the verifiable credential types. So we have a standard list of types which includes verifiable credential and structured credential. We need to add onto that the verifiable capability authorization type. And once we have, again, the content and the label, then we can stuff it into the envelope and attach the label. Once we have the envelope containing the content and the label on the outside, we want to make sure that neither the content nor the label is ever altered. And so we do that by computing a proof. So again, because the envelope here is a TSL structure, we can simply get the JSON representation of it. We can compute a SHA-256 hash of that using one of our helper functions. And then we've got a helper function that will compute a proof of the hash. And then we're going to take that proof and we're going to stuff it, the hash and the proof, and we're going to stuff it into the envelope seal. Let's just backtrack for a moment and look at what compute hash looks like, compute hash proof looks like. So we have a helper here that takes the hash, it takes the secret key of the person issuing the VCA and a nonce. And we're using the intrinsic OK API Oberon library, and there's a two-step process to create a proof. We create a token by passing in the hash the SHA-256 hash and the secret key. We get a token, and that token again is used down here to actually create the proof itself. And so we pass in the hash, the nonce, and the token. The sort of the internal reasoning for the separation of these two functions is just specific to the Oberon library. And on the proof that's returned, we want to get the proof element, turn it into a base 64 representation, and that will actually be the string that we will stuff into our envelope seal. So if we go back here, we get that proof of the hash, we get that proof, and the next thing we want to do is take the envelope and stick or glue that proof to the outside. And so we do that by calling the sealed envelope constructor, and it returns us a sealed envelope. Again, if we look at the sealed envelope TSL definition, it takes a proof and an envelope and a proof, and the constructor simply assigns those for us. So we did some benchmarking here for performance, and we found that creating a proof of the hash is sometimes an order of magnitude faster. Our helper method here that's creating the VCA credential now has that as a strongly typed a strongly typed structure. And when we go back here to our program, that's what we're receiving here. So we have a VCA credential. And by turning that VCA credential into a string, we get the JSON representation. So now we have a JSON payload that we can then use the VCTPS DIDCOMM protocol to send that VCA from the originator to one or more or several recipients. That's all we're going to cover here in Prototype 5. There's actually more involved. Just by looking at the Solution Explorer, you can see there's a lot more code here, but this is really the main goal, the main subject of Demo 5. Being able to illustrate using the structured credential programming model beyond simply defining the DIDCOMM agent, but to actually use it to create our verifiable credentials, to create our structured credentials. And in this particular example, we have illustrated how to create a verifiable capability authorization as a VC. Thank you.